Hey everyone, tonight we're exploring one of the most profound mysteries in all of cosmology, dark matter, the invisible architecture that shapes our entire universe. Before we settle in for this deep cosmic journey, take a moment to like this if you enjoy these explorations of the cosmos, and please subscribe if you haven't already. It really helps us grow this wonderful community of stargazers and cosmic contemplators. Let me know in the comments where you're listening from and what time it is for you. I always find it fascinating how our global community gathers to contemplate the cosmos together, united by our shared sense of wonder at the universe's deepest mysteries. Now get comfortable, dim those lights, and perhaps step outside if you can to look up at the stars. Tonight, we're not chasing dramatic space battles or alien encounters. Instead, we're going to examine something much more profound and peaceful: the invisible scaffolding that holds everything together, the dark matter that comprises over 80% of all matter in the universe, yet remains completely invisible to our eyes and instruments. We're going to explore how this mysterious substance weaves the cosmic web, guides the formation of galaxies, and creates the large-scale structure of everything we can see. Let's begin our gentle journey into the infinite, into the realm of the invisible that makes the visible possible. As you settle in tonight, imagine looking up at the night sky and seeing only a fraction of what's actually there. Every star, every galaxy, every nebula you can observe, whether with your naked eye or the most powerful telescopes, represents less than 20% of the matter that actually exists. The rest is invisible, detectable only through its gravitational influence, like a ghost that moves furniture but can never be seen. This is dark matter, and tonight we're going to explore its hidden architecture with the patience and wonder it deserves. The story of dark matter begins not with dramatic discoveries or eureka moments, but with careful observations and quiet puzzles that accumulated over decades. In the 1930s, astronomer Fritz Zwicky was studying the Coma Cluster, a collection of over 1,000 galaxies bound together by gravity. As he measured the motions of these galaxies, he encountered something deeply puzzling. The galaxies were moving too fast. According to the amount of visible matter he could observe, the cluster should have flown apart long ago. Yet there it was, stable and bound together, suggesting that some invisible mass was providing the additional gravitational glue needed to hold it all together. Zwicky called this invisible mass Dunkel Materie, dark matter. But his discovery was so far ahead of its time that it was largely ignored for decades. The universe, it seemed, was keeping a secret that wouldn't be fully appreciated until much later. Fast forward to the 1970s, and astronomer Vera Rubin was studying something much closer to home: the rotation of spiral galaxies. Using the most advanced spectroscopic techniques of her time, she measured how fast stars were orbiting around the centers of galaxies like our own Milky Way. What she found defied all expectations and would eventually revolutionize our understanding of the cosmos. According to Newton's laws of gravity, stars farther from a galaxy's center should orbit more slowly, just as planets farther from the sun take longer to complete their orbits. This creates what astronomers call a Keplerian rotation curve. Orbital speed decreases with distance from the center. But Rubin's observations showed something completely different. Stars in the outer regions of galaxies were moving just as fast as those closer to the center, creating what's known as a flat rotation curve. This was like discovering that Pluto orbits the Sun at the same speed as Mercury, a complete violation of everything we thought we knew about gravity and orbital mechanics. The only way to explain these observations was to invoke the presence of vast amounts of invisible matter, far more than all the visible stars and gas combined. This dark matter had to be distributed in a spherical halo around each galaxy, providing the gravitational influence needed to keep the outer stars moving at their observed speeds. But dark matter's influence extends far beyond individual galaxies. To understand its true cosmic role, we need to journey back to the very beginning of the universe, to a time when the cosmos was young and the seeds of all future structure were being planted. In the early universe, roughly 380,000 years after the Big Bang, the cosmos had cooled enough for the first atoms to form. This period, known as recombination, marked the moment when the universe became transparent to light for the first time. The cosmic microwave background radiation that we observe today is the afterglow of this moment, carrying with it the imprint of tiny density fluctuations that existed in the primordial plasma. These fluctuations were incredibly small, variations in density of only about 1 part in 100,000. Yet they were the seeds from which all cosmic structure would eventually grow. Here's where dark matter played its crucial role. Unlike ordinary matter, dark matter doesn't interact with light or ordinary matter through the electromagnetic force. This means it was immune to the radiation pressure that was smoothing out the ordinary matter in the early universe. While ordinary matter was being pushed around by photons, dark matter was already beginning to clump together under its own gravity. It formed the first gravitational wells, the first seeds of structure in the cosmos. These dark matter clumps then began to attract ordinary matter, which fell into the gravitational wells that dark matter had already carved out. In this way, dark matter served as the scaffolding upon which all visible structure would eventually be built. Think of it like the framework of a building under construction. The dark matter provides the invisible steel beams and support structures, while ordinary matter, the stuff of stars and planets and us, is like the walls and decorations that make the building visible and livable. Without the dark matter framework, none of the visible structure could exist. As the universe continued to expand and cool, these dark matter clumps grew larger and more massive through a process called hierarchical structure formation. Smaller clumps merged to form larger ones, which in turn merged to form even larger structures. This process continued for billions of years, creating the cosmic web, a vast network of dark matter filaments stretching across the universe, connected by nodes where the densest concentrations of dark matter and ordinary matter would eventually form galaxy clusters. The cosmic web is perhaps the most beautiful and elegant structure in the universe, though it remains largely invisible to us. Picture a three-dimensional spider's web stretching across space with filaments of dark matter connecting dense nodes separated by vast empty voids. Along these filaments, ordinary matter flows like water through cosmic rivers, eventually collecting in the nodes where it ignites to form stars and galaxies. Computer simulations of this process reveal the cosmic web in all its glory. These simulations start with the tiny fluctuations observed in the cosmic microwave background and evolve them forward through cosmic time using our understanding of gravity and the properties of dark matter. The result is a foam-like structure of interconnected filaments and nodes, with the largest structures being superclusters of galaxies connected by filaments that can stretch for hundreds of millions of light years. The Millennium simulation, one of the most detailed computer models of cosmic structure formation, required months of processing time on some of the world's most powerful supercomputers. It followed the evolution of over 10 billion dark matter particles through cosmic time, revealing how the smooth early universe evolved into the complex web of structure we see today. The simulation shows dark matter halos of every size, from tiny dwarf galaxy halos to massive cluster halos, all connected by the cosmic web. What's remarkable about these simulations is how well they match what we observe in the real universe. The distribution of galaxies we see through our telescopes follows the same patterns predicted by the dark matter simulations. Galaxies are found along filaments. They cluster at the intersections of these filaments, and they avoid the vast, empty voids between them. This agreement between simulation and observation is one of the strongest pieces of evidence for the existence of dark matter. The cosmic web is not static, but dynamic, constantly evolving as structure continues to grow through gravitational collapse. Dark matter halos are constantly merging and accreting new material, while gas flows along the filaments toward the densest nodes. This process is ongoing even today, billions of years after the first structures formed. Our own local group of galaxies, containing the Milky Way, Andromeda, and dozens of smaller galaxies, sits at the intersection of several cosmic web filaments. We're part of a larger structure called the Virgo supercluster, which itself is part of an even larger structure called the Laniakea supercluster. These nested hierarchies of structure all trace back to the original dark matter scaffolding that formed in the early universe. The dark matter halo surrounding our own Milky Way galaxy extends far beyond the visible disk of stars. This halo is roughly spherical and extends to at least 300,000 light-years from the galactic center, more than twice the diameter of the visible galaxy. It contains roughly 10 times more mass than all the stars in the Milky Way combined, yet it's completely invisible except for its gravitational effects. Within this vast halo, astronomers have discovered streams of stars that trace the orbits of small galaxies that have been torn apart by the Milky Way's gravity. These stellar streams are like cosmic fossils, preserving the history of how our galaxy has grown through mergers and accretion over cosmic time. The streams follow the gravitational contours of the dark matter halo, revealing its shape and structure in exquisite detail. The Sagittarius stream is one of the most prominent of these stellar streams, wrapping around the Milky Way like a ribbon. It's the remnant of a dwarf galaxy that has been slowly torn apart by tidal forces as it orbited our galaxy. The stream extends for more than 360 degrees around the sky, creating a nearly complete circle of stars that follows the gravitational architecture of the dark matter halo. But dark matter's influence extends beyond just providing gravitational scaffolding. It also plays a crucial role in regulating star formation and galaxy evolution. The depth of a galaxy's dark matter potential well determines how much gas it can retain, which in turn determines how many stars it can form. Galaxies in more massive dark matter halos can hold on to more gas and continue forming stars for longer periods, while those in less massive halos may have their gas stripped away by various processes. This relationship between dark matter and visible matter is beautifully illustrated in the cosmic web itself. The most massive dark matter halos, located at the nodes of the web, host the most massive galaxies and galaxy clusters. These are the cosmic cities, bustling with activity as gas flows in along the filaments and ignites to form new stars. The filaments themselves host smaller galaxies, strung along the cosmic web like beads on a string. And the vast voids between filaments are nearly empty, containing only a few small, isolated galaxies. The cosmic web also channels the flow of intergalactic gas, creating vast rivers of material that feed the growth of galaxies. This gas is heated as it falls into dark matter, potential wells, sometimes reaching temperatures of millions of degrees. In the most massive galaxy clusters, this hot gas becomes so luminous in X-rays that it outshines all the stars in the cluster galaxies combined. As we contemplate the cosmic web and its dark matter architecture, we're reminded of our place in this vast structure. The atoms in our bodies were forged in the hearts of stars that formed within dark matter halos. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of these elements were created through stellar nucleosynthesis within galaxies that could not have formed without dark matter's gravitational scaffolding. In a very real sense, we are children of the cosmic web. Our existence depends on the invisible architecture that has shaped the universe for billions of years. Every breath we take, every heartbeat, every thought we think is possible because dark matter carved out the gravitational wells that allowed ordinary matter to collect and form the first stars and galaxies. The beauty of dark matter lies not just in its cosmic role, but in its fundamental mystery. Despite decades of searching, we still don't know what dark matter actually is. We know it's there through its gravitational effects. We know it doesn't interact with light, and we know it's not made of ordinary atoms. But its true nature remains one of the greatest puzzles in modern science. Leading candidates for dark matter include exotic particles predicted by theories beyond the standard model of particle physics. These particles would have been created in the early universe and would interact only through gravity and possibly the weak nuclear force. They would be their own antiparticles, occasionally annihilating with each other to produce detectable radiation. Scientists around the world are building increasingly sensitive detectors to try to catch these elusive particles. The search for dark matter has led to some of the most sophisticated experiments ever conceived. Deep underground, shielded from cosmic rays and other interference, scientists have placed detectors cooled to temperatures colder than outer space. These detectors are waiting for the incredibly rare collision between a dark matter particle and an atomic nucleus, an event that would produce a tiny flash of light or a minuscule amount of heat. Other experiments are looking for the products of dark matter annihilation in space. If dark matter particles do occasionally destroy each other, they might produce gamma rays, neutrinos, or other particles that we can detect. Observations of the galactic center, where dark matter should be most concentrated, are searching for these telltale signs of dark matter interactions. The Large Hadron Collider at CERN is also joining the hunt, attempting to create dark matter particles in high-energy collisions. If dark matter particles can be produced in the laboratory, they would immediately escape the detector, leaving behind only a characteristic signature of missing energy and momentum. As we journey deeper into the night and deeper into our contemplation of dark matter, we're struck by the profound humility it imposes on our understanding of the universe. For all our technological achievements, for all our scientific knowledge, we remain largely ignorant about the substance that dominates the cosmos. The visible universe, everything we can see with our eyes and telescopes, is just the tip of the iceberg, a small fraction of what's actually out there. This cosmic humility is both unsettling and liberating. It reminds us that the universe is far stranger and more wonderful than we ever imagined. It tells us that reality extends far beyond our everyday experience, into realms that challenge our most basic assumptions about the nature of matter and space. Dark matter also reminds us of the unity of the cosmos. The same invisible scaffolding that shapes the largest structures in the universe also influences the formation of our own galaxy, our own solar system, and ultimately, our own existence. We are connected to the cosmic web, not just through the atoms in our bodies, but through the very architecture of space and time. As we continue our journey through the night, moving ever deeper into the realm of dark matter, we're preparing to explore even more profound mysteries. We'll discover how dark matter halos grow and evolve, how they interact with each other and with ordinary matter, and how they shape the destiny of galaxies across cosmic time. We'll explore the subtle dance between dark matter and dark energy, the two mysterious components that together dominate the universe. The cosmic web stretches out before us, its invisible filaments connecting every corner of the observable universe. Along these filaments, dark matter flows like an invisible river, carrying with it the seeds of future structure. Where the filaments intersect, new galaxies are born from the collapse of primordial gas clouds. Where they stretch across the voids, they maintain the delicate balance that keeps the cosmic web stable across billions of years. In the vast spaces between galaxies, dark matter halos continue their slow dance of merger and accretion. Smaller halos are absorbed by larger ones, while the largest halos grow to become the sites of massive galaxy clusters. This process of hierarchical structure formation is still ongoing today, though it proceeds at a much slower pace than in the early universe when the cosmic web was young and actively growing. The patience required to understand dark matter matches the patience of the universe itself. Just as cosmic structures grow slowly over billions of years, our understanding of dark matter has evolved gradually through decades of careful observation and theoretical work. Each new discovery adds another piece to the puzzle, slowly revealing the true nature of the invisible universe. As we prepare to transition into the second part of our journey, we find ourselves at the edge of even greater mysteries. We've explored the scaffolding that dark matter provides, the cosmic web it creates, and the gravitational wells it carves out for ordinary matter. But there are deeper questions still to be answered, more profound mysteries yet to be explored. The dark matter that surrounds us, that fills the space between galaxies, that shapes the very fabric of the cosmos, this invisible presence continues to guard its secrets even as it reveals its influence everywhere we look. In the gentle rotation of spiral galaxies, in the binding of galaxy clusters, in the flow of gas along cosmic filaments, dark matter's signature is written across the universe in letters of gravity and light. Tonight, as we pause at the midpoint of our journey, we're reminded that the universe is far more mysterious and wonderful than we ever imagined. The dark matter that fills the cosmos is not just a scientific curiosity, but a fundamental component of reality itself. It shapes the universe on the largest scales while remaining invisible to our most sensitive instruments. It connects us to the cosmic web while maintaining its essential mystery. As we continue our exploration, we'll delve even deeper into the nature of dark matter, exploring its role in galaxy formation, its interaction with ordinary matter, and its ultimate fate in the far future of the universe. We'll discover how dark matter halos merge and evolve, how they channel the flow of cosmic gas, and how they shape the destiny of galaxies across the eons. The invisible architecture of the universe awaits our continued exploration, patient and eternal, ready to reveal its secrets to those who approach with wonder and reverence. The cosmic web stretches out before us, its dark matter filaments connecting every corner of the observable universe, weaving together the fabric of space and time itself. In this moment of quiet contemplation, we find ourselves part of something much larger than ourselves, part of the cosmic web, part of the invisible architecture that shapes everything we see and everything we are. The dark matter that fills the universe is not separate from us, but intimately connected to our existence, our planet, our galaxy, and our cosmic destiny. As we prepare to continue our journey deeper into the mystery of dark matter, we carry with us the profound realization that we are explorers of the invisible, seekers of the hidden architecture that shapes reality itself. The universe has entrusted us with the capacity to wonder, to question, to slowly unravel the mysteries that surround us on every side. The cosmic web awaits, patient and eternal, ready to reveal its secrets to those who approach with wonder and humility. In the second part of our journey, we'll explore how this invisible architecture continues to shape the universe, how it interacts with the matter we can see, and how it holds the keys to understanding the deepest mysteries of existence itself. But before we venture into those deeper mysteries, let us pause to appreciate the sheer scale and elegance of what we've discovered so far. The dark matter that permeates the universe is not just a passive component, but an active architect, constantly shaping and reshaping the cosmic landscape through its gravitational influence. Every galaxy we observe, every star cluster, every nebula exists where it does because of the invisible scaffolding that dark matter has constructed over billions of years. The cosmic web that dark matter has woven spans distances that challenge human comprehension. Individual filaments can stretch for hundreds of millions of light years, connecting galaxy clusters separated by vast cosmic distances. These filaments are not empty highways, but active conduits, channeling the flow of gas and energy that powers the ongoing formation of new stars and galaxies. Along their length, smaller structures form and evolve, creating a hierarchy of cosmic architecture that extends from the smallest dark matter subhalos to the largest superclusters. Within our own cosmic neighborhood, the local group of galaxies, we can observe this hierarchy in action. The Milky Way and Andromeda galaxies are the two largest members of the local group, each surrounded by its own extensive dark matter halo. These halos extend far beyond the visible boundaries of the galaxies themselves, creating spherical regions of gravitational influence that encompass dozens of smaller satellite galaxies. The satellite galaxies of the Milky Way, including the large and small Magellanic Clouds, the Sagittarius Dwarf Galaxy, and numerous other small companions, all orbit within our galaxy's dark matter halo. Their orbits are shaped by the gravitational contours of this invisible structure, creating complex patterns of motion that astronomers are only beginning to understand fully. Some of these satellite galaxies have been completely disrupted by the Milky Way's gravity, their stars scattered into long streams that wrap around our galaxy like cosmic ribbons. The Sagittarius stream, which we mentioned earlier, is just one of many such streams that have been discovered in recent years. Each stream tells a story of cosmic cannibalism, of larger structures growing by consuming smaller ones, all orchestrated by the invisible hand of dark matter. The process of galaxy formation within dark matter halos is a delicate dance between gravity and physics. As dark matter clumps together under its own gravitational attraction, it creates potential wells that attract ordinary matter. This ordinary matter, primarily hydrogen and helium gas from the early universe, falls into these wells and begins to heat up due to gravitational compression. Initially, this gas is too hot to form stars directly. It must first cool down, radiating away its thermal energy through various processes. In smaller dark matter halos, this cooling happens relatively quickly, allowing gas to condense and form the first stars within a few 100 million years of the Big Bang. These were the first galaxies, small and compact, dominated by massive, short-lived stars that ended their lives in spectacular supernova explosions. In larger dark matter halos, the cooling process is more complex and takes longer. The gas that falls into these halos is heated to such high temperatures that it takes billions of years to cool sufficiently for star formation. This creates a natural segregation in the universe. Smaller halos host smaller galaxies that formed their stars early and quickly, while larger halos host larger galaxies that formed their stars more gradually over cosmic time. This relationship between dark matter halo mass and galaxy properties is one of the most fundamental scaling relations in astronomy. It explains why we observe such a wide diversity of galaxy types, from tiny dwarf galaxies containing only a few million stars to massive elliptical galaxies containing hundreds of billions of stars. Each type of galaxy reflects the properties of the dark matter halo in which it formed. The cosmic web also plays a crucial role in determining galaxy properties through a process called environmental effects. Galaxies that form at the intersections of multiple filaments in the dense nodes of the cosmic web experience a very different environment than galaxies that form along individual filaments or in the sparse regions between filaments. In dense environments, galaxies are more likely to interact with each other through gravitational encounters. These interactions can trigger bursts of star formation as gas is compressed and heated, or they can strip gas away from galaxies entirely, quenching star formation. The hot gas that fills the space between galaxies in dense clusters can also prevent new gas from falling into galaxy halos, effectively starving them of the fuel needed to form new stars. In contrast, galaxies that form in less dense environments, along individual filaments or in sparse regions, can continue to accrete gas from their surroundings for much longer periods. This allows them to maintain steady rates of star formation over cosmic time, creating the spiral galaxies with active star formation that we observe in the present-day universe. The Milky Way itself is an example of a galaxy that formed in a relatively sparse environment. Our local group sits in a region of space that is less dense than the massive galaxy clusters found at the nodes of the cosmic web. This has allowed our galaxy to continue forming stars at a steady rate throughout its history, maintaining the spiral structure and active star formation regions that make it such a beautiful and dynamic system. But even in this relatively sparse environment, the influence of dark matter is profound. The dark matter halo that surrounds the Milky Way is not a static structure, but a dynamic, evolving system that continues to grow through the accretion of smaller halos and the ongoing inflow of gas from the cosmic web. This growth is slow and gradual, but it has profound implications for our galaxy's future evolution. Astronomers have used computer simulations to model the future evolution of the Milky Way's dark matter halo. These simulations suggest that our galaxy will continue to grow slowly over the next several billion years, accreting additional dark matter from the cosmic web and occasionally merging with smaller satellite galaxies. The most dramatic event in our galaxy's future will be the collision and merger with the Andromeda Galaxy, expected to occur in about 4.5 billion years. This merger will be a spectacular demonstration of dark matter's role in cosmic evolution. The two galaxies' dark matter halos will interact first, passing through each other and then gradually merging to form a single, larger halo. The visible components of the galaxies, their stars and gas, will follow more complex trajectories, creating tidal tails and spiral structures as they respond to the changing gravitational field. The merger will trigger intense bursts of star formation as gas clouds collide and compress, temporarily increasing the star formation rate by factors of 10 or more. Eventually, the two galaxies will settle into a single, massive elliptical galaxy, exhausting most of their gas supply and entering a quieter phase of evolution dominated by the aging of their stellar populations. This process of galaxy mergers is not unique to the Milky Way and Andromeda. It's a fundamental aspect of cosmic evolution, driven by the hierarchical growth of dark matter structure. Throughout the universe, galaxies are constantly interacting, merging, and evolving, all under the guidance of the invisible dark matter framework that surrounds them. The cosmic web itself is also evolving, though on much longer timescales than individual galaxy mergers. The filaments that connect galaxy clusters are slowly growing and strengthening as more dark matter flows along them. The nodes where filaments intersect are becoming more massive and dense, creating ever larger galaxy clusters and superclusters. At the same time, the expansion of the universe is stretching the cosmic web, gradually increasing the distances between its components. This expansion is accelerating due to the influence of dark energy, the mysterious force that makes up about 70% of the universe's total energy density. The interplay between dark matter's gravitational attraction and dark energy's repulsive effect determines the ultimate fate of cosmic structure. In the current epoch, dark energy is beginning to dominate over dark matter on the largest scales. This means that the era of vigorous structure formation is coming to an end. New galaxy clusters are still forming, but at a much slower rate than in the past. The cosmic web is entering a mature phase, where existing structures continue to evolve, but few new large-scale structures are being created. This transition from a dark matter-dominated to a dark energy-dominated universe represents one of the most profound changes in cosmic history. It marks the end of the structure formation era and the beginning of a new phase in the universe's evolution. Understanding this transition is crucial for predicting the ultimate fate of the cosmos and our place within it. The study of dark matter has also revealed profound connections between the physics of the very large and the very small. The properties of dark matter particles, whatever they may be, were determined by the conditions that existed in the early universe when these particles were first created. The cosmic web that we observe today is thus a fossil record of the universe's earliest moments, preserving information about the fundamental physics that governed the cosmos when it was less than a second old. This connection between cosmology and particle physics has led to an intense search for dark matter particles in laboratory experiments. If we can identify and study these particles directly, we may be able to learn not just about dark matter itself, but about the fundamental nature of matter and energy in the universe. The search for dark matter particles has pushed the boundaries of experimental physics to new extremes. Deep underground, in mines and tunnels shielded from cosmic rays, scientists have constructed detectors of unprecedented sensitivity. These experiments are looking for the incredibly rare interactions between dark matter particles and ordinary matter, events so subtle that they can be overwhelmed by the background radiation from natural radioactivity or cosmic ray interactions. The Xenon experiment, located beneath the Gran Sasso mountain in Italy, uses over 3 tons of liquid xenon, cooled to extremely low temperatures. When a dark matter particle collides with a xenon nucleus, it produces a tiny flash of light and a small amount of ionization. These signals are detected by sensitive photomultiplier tubes and electronics, allowing scientists to identify potential dark matter interactions among the billions of other events that occur in the detector. Similar experiments are operating around the world, each using different detection techniques and target materials. The Lux Zeppelin experiment in South Dakota uses a similar liquid xenon approach, but with even greater sensitivity. The CDMS experiment uses crystals of silicon and germanium cooled to temperatures just above absolute zero, detecting the tiny amounts of heat deposited by dark matter collisions. So far, these experiments have not definitively detected dark matter particles, but they have placed increasingly stringent limits on the properties that such particles must have. These limits are beginning to constrain theoretical models of dark matter, forcing physicists to consider new possibilities for the nature of the universe's invisible component. Other experiments are looking for the products of dark matter annihilation or decay. If dark matter particles are their own antiparticles, they should occasionally collide and annihilate with each other, producing gamma rays, neutrinos, or other detectable particles. The centers of galaxies, where dark matter is most concentrated, are prime targets for these searches. The Fermi Gamma Ray Space Telescope has been surveying the sky for signs of dark matter annihilation, looking for characteristic signatures in the gamma ray spectrum. Some intriguing signals have been detected, including an excess of gamma rays from the galactic center that could potentially be explained by dark matter annihilation. However, these signals are still being studied and debated, as they could also be produced by other astrophysical processes. Ground-based gamma-ray telescopes, such as the High Energy Stereoscopic System, HESS, in Namibia, and the Major Atmospheric Gamma Imaging Cherenkov, MAGIC, telescope in Spain, are also contributing to the search for dark matter. These instruments can detect the faint flashes of light produced when high-energy gamma rays interact with Earth's atmosphere, providing another window into the possible annihilation products of dark matter particles. The search for dark matter has also extended to particle accelerators, where scientists are attempting to create dark matter particles in high-energy collisions. The Large Hadron Collider at CERN, the world's most powerful particle accelerator, is conducting experiments designed to produce dark matter particles and study their properties. In these experiments, protons are accelerated to nearly the speed of light and collided with each other, creating conditions similar to those that existed in the early universe. If dark matter particles are produced in these collisions, they would immediately escape the detector without leaving a direct trace. However, their presence could be inferred from the missing energy and momentum in the collision products. The ATLAS and CMS experiments at the LHC have been searching for such signatures for over a decade, gradually improving their sensitivity and exploring new theoretical models. While no definitive evidence for dark matter production has been found, these experiments have provided valuable insights into the possible properties of dark matter particles and the fundamental forces that govern their interactions. The quest to understand dark matter has also led to new theoretical insights about the nature of space and time itself. Some theories propose that dark matter is not made of particles at all, but rather represents a modification of gravity itself on cosmic scales. These modified gravity theories attempt to explain the observed effects of dark matter through changes to Einstein's general theory of relativity. However, these alternative theories face significant challenges in explaining the full range of observations that point to dark matter's existence. The cosmic microwave background radiation, the large-scale structure of the universe, and the behavior of galaxy clusters during collisions all provide strong evidence for the existence of a non-interacting form of matter that behaves exactly as dark matter is predicted to behave. The interplay between observation and theory in dark matter research represents one of the most exciting frontiers in modern science. Each new observation provides additional constraints on theoretical models, while new theoretical insights suggest new observational tests. This ongoing dialogue between theory and experiment is gradually narrowing down the possible explanations for dark matter's nature. As we delve deeper into the mystery of dark matter, we begin to appreciate the profound implications of its existence for our understanding of the universe. Dark matter is not just another component of the cosmos, but a fundamental aspect of reality that shapes everything we see and experience. It connects the physics of the very large to the physics of the very small, linking the formation of galaxies to the behavior of subatomic particles. The cosmic web that dark matter has woven is not just a static structure, but a dynamic, evolving framework that continues to shape the universe around us. Every galaxy, every star, every planet exists within this invisible architecture, their properties and evolution determined by the patient work of dark matter over cosmic time. As we continue our journey through the night, we carry with us the profound realization that we are not just observers of the universe, but participants in its grand design. The dark matter that fills the cosmos is not separate from us, but intimately connected to our existence, our planet, our galaxy, and our cosmic destiny. We are children of the cosmic web, our atoms forged in stellar furnaces, our lives sustained by the invisible scaffolding that dark matter provides. The mystery of dark matter remains one of the greatest challenges in modern science, but it is also one of the most beautiful and inspiring. It reminds us that the universe is far stranger and more wonderful than we ever imagined, filled with invisible architectures and hidden connections that challenge our understanding of reality itself. As we prepare to continue our exploration into the second part of our journey, we carry with us the wonder and humility that dark matter inspires, ready to delve even deeper into the cosmic mysteries that surround us on every side. As we continue our journey deeper into the mystery of dark matter, we find ourselves at the threshold of even more profound discoveries. The invisible scaffolding we explored in our first part, the cosmic web of dark matter, filaments, and nodes, is not a static structure, but a dynamic, ever-evolving architecture that continues to shape the universe around us. Tonight, we'll explore how this invisible matter dances through space and time, orchestrating the formation of galaxies, channeling the flow of cosmic gas, and ultimately determining the fate of all visible matter in the universe. The story of dark matter's cosmic dance begins with understanding that what we perceive as empty space is actually teeming with invisible activity. Every cubic meter of space in our galaxy contains roughly one dark matter particle, each moving at speeds of hundreds of kilometers per second. These particles don't interact with each other or with ordinary matter through any force except gravity, making them like ghosts that pass through walls without leaving a trace. Yet it's precisely this ghostly nature that makes dark matter so effective at its cosmic role. While ordinary matter can be heated, compressed, and scattered by radiation pressure, dark matter remains immune to these influences. It responds only to gravity, making it the perfect medium for building the large-scale structure of the universe. Like a patient architect working on a cosmic time scale, dark matter has been constructing the invisible framework that supports all visible matter for nearly 14 billion years. As you rest tonight, billions of dark matter particles are streaming through your body at this very moment, completely unnoticed. Each particle follows an orbit that was established billions of years ago when the cosmic web was young. They carry with them the memory of cosmic time, the accumulated history of gravitational interactions spanning the entire age of the universe. In a very real sense, you are swimming through an ocean of invisible matter that connects you to the deepest structures of the cosmos. The dance of dark matter unfolds on multiple scales simultaneously. On the largest scales, dark matter flows along the cosmic web, streaming from lower density regions toward higher density nodes. These flows are not random, but follow the gravitational contours carved out by the primordial density fluctuations in the early universe. The result is a vast network of streams and rivers of dark matter, invisible to our eyes, but detectable through their gravitational effects on the galaxies they encounter. Within galaxy clusters, dark matter performs a more complex choreography. Computer simulations reveal that dark matter halos are constantly merging, creating spectacular gravitational ballets that unfold over hundreds of millions of years. When two massive dark matter halos collide, they don't simply merge immediately like two drops of water. Instead, they pass through each other, their particles interacting only through gravity, creating complex patterns of oscillation and eventual merger. The bullet cluster provides one of the most dramatic examples of this cosmic dance. This system consists of two galaxy clusters that collided roughly 150 million years ago, creating a natural laboratory for studying dark matter's behavior. What makes the bullet cluster so important is that we can observe both the dark matter and the ordinary matter separately, watching how they behave differently during the collision. When the two clusters collided, their dark matter halos passed through each other largely unaffected, like two swarms of ghosts passing through each other without interaction. But the ordinary matter, the hot gas that fills the space between galaxies, crashed together violently, creating shock waves and heating the gas to temperatures of tens of millions of degrees. The result is a system where the dark matter, detected through gravitational lensing, is offset from the ordinary matter, visible in X-ray images of the hot gas. This separation of dark matter and ordinary matter during the collision provides compelling evidence for dark matter's existence and its collisionless nature. It's like watching a cosmic magic trick where the invisible performer reveals itself by moving the props in impossible ways. The bullet cluster shows us that dark matter really is a separate component of the universe, not just a modification of our understanding of gravity. The gravitational lensing effects that reveal dark matter's presence are themselves a beautiful demonstration of Einstein's general theory of relativity. Dark matter's gravity warps the fabric of space-time, bending the paths of light rays from distant galaxies. This creates a cosmic magnifying glass effect, distorting and magnifying the images of background galaxies. By carefully measuring these distortions, astronomers can map the distribution of dark matter with remarkable precision. The resulting dark matter maps reveal a universe that looks nothing like what we see with ordinary telescopes. Instead of the familiar patterns of stars and galaxies, we see a cosmic web of ghostly filaments and nodes, a shadow universe that exists parallel to our own. The visible galaxies are like decorations hung on this invisible framework, their positions and motions determined by the dark matter scaffolding that supports them. These gravitational lensing studies have revealed dark matter structure on scales ranging from individual galaxy halos to massive galaxy clusters. The most detailed maps show how dark matter is distributed within clusters, revealing complex substructures and asymmetries that reflect the violent merger history of these cosmic behemoths. Some clusters show multiple dark matter peaks, evidence of ongoing mergers between smaller subclusters. Within individual galaxies, dark matter creates what astronomers call the halo. This spherical distribution of invisible matter extends far beyond the visible disk of stars, creating a gravitational well that holds the galaxy together. The halo is not uniform, but has structure, with subhalos and streams created by the accretion and disruption of smaller dark matter clumps over cosmic time. Our own Milky Way galaxy sits within such a dark matter halo, and we're actually moving through it at a speed of about 200 kilometers per second as we orbit the galactic center. This means that every second, roughly 100 billion dark matter particles pass through each of us, completely unnoticed. We are, in a very real sense, swimming through an ocean of invisible matter, feeling its presence only through the gravitational effects that keep our galaxy stable and our solar system in its orbit. The dark matter halo that encompasses our galaxy is not a simple, smooth sphere, but a complex structure shaped by billions of years of cosmic evolution. Computer simulations suggest that it contains thousands of smaller subhalos, the remnants of dark matter clumps that fell into our galaxy's gravitational well over cosmic time. Some of these subhalos may still contain small populations of stars, forming the dwarf satellite galaxies that orbit the Milky Way. Others may be completely dark, invisible, except for their gravitational influence. The search for these dark subhalos represents one of the most challenging frontiers in observational astronomy. They are too small and dim to be detected directly, but their gravitational effects might be measurable through careful studies of stellar motions or through gravitational lensing of background stars. Finding and characterizing these invisible structures would provide crucial tests of our understanding of dark matter and the hierarchical formation of cosmic structure. Recent studies using the precise measurements from the Gaia Space Telescope have begun to reveal the three-dimensional structure of our galaxy's dark matter halo in unprecedented detail. By tracking the motions of millions of stars, astronomers can map the gravitational field created by the invisible matter that dominates our galaxy's mass. These studies have revealed streams and substructures that were previously unknown, each one a fossil record of ancient mergers and interactions. The Sagittarius stream, which we encountered earlier, is just one of many stellar streams that crisscross our galactic neighborhood. The Helmi stream, the Sequoia stream, the Gaia Enceladus stream, each of these poetic names marks the remnants of ancient galaxies that helped build the Milky Way we know today. Each stream follows its own orbit through the dark matter halo, creating a complex network of stellar archaeology that astronomers are only beginning to map and understand. These stellar streams reveal the dynamic nature of our galaxy's dark matter halo. Far from being a static structure, the halo is constantly evolving as it accretes new material from the cosmic web and merges with smaller dark matter clumps. This ongoing evolution is still shaping our galaxy today, billions of years after its initial formation. The streams we observe are just the most recent chapters in a long history of cosmic growth and change. The search for dark matter particles continues in laboratories around the world, each experiment pushing the boundaries of sensitivity and exploring new regions of theoretical possibility. The next generation of detectors promises even greater sensitivity, using larger targets, better shielding, and more sophisticated analysis techniques. Advanced cryogenic systems cool detectors to temperatures just thousandths of a degree above absolute zero, while underground locations shield experiments from cosmic rays and other sources of background interference. The Darwin experiment, currently under development, will use 10 tons of liquid xenon to search for dark matter interactions, more than 3 times larger than any current detector. This massive scale will provide unprecedented sensitivity to dark matter particles, potentially finally revealing the nature of the invisible substance that dominates our universe. The detector will be so sensitive that it will be able to detect neutrinos from the sun, requiring sophisticated techniques to distinguish genuine dark matter signals from this astrophysical background. Other future experiments will explore different detection strategies. The DAMIC experiment uses charge-coupled devices similar to those in digital cameras, but operated at extremely cold temperatures to detect the tiny amounts of energy deposited by dark matter collisions. The CREST-T experiment uses crystal detectors that can simultaneously measure both the heat and light produced by particle interactions, providing additional ways to identify dark matter signals. Some experiments are looking for annual modulation signals as the Earth orbits through the dark matter halo. As our planet moves through the galaxy, it should encounter more dark matter particles when moving in the same direction as the solar system's motion through the halo, and fewer when moving in the opposite direction. This creates a subtle, annual variation in the dark matter detection rate that could provide a smoking gun signature of discovery. Directional detection represents another frontier in the search for dark matter. If we could measure not just the energy, but also the direction of recoiling nuclei hit by dark matter particles, we could potentially see the motion of our solar system through the dark matter halo. Several experiments are developing techniques to track the paths of recoiling nuclei in 3 dimensions, using everything from supercooled liquid droplets to gaseous detectors with exquisite spatial resolution. Space-based searches for dark matter continue to evolve as well. The Alpha Magnetic Spectrometer aboard the International Space Station has been measuring cosmic ray particles for over a decade, searching for the signatures of dark matter annihilation in the form of excess positrons or antiprotons. The data from AMS has revealed some intriguing features in the cosmic ray spectrum, but their interpretation remains a subject of debate among physicists. Future space missions may include dedicated dark matter telescopes optimized for detecting the gamma rays or other particles that might be produced when dark matter particles destroy each other. The Cherenkov Telescope Array, currently under construction, will be the world's largest ground-based gamma-ray observatory with unprecedented sensitivity to the high-energy photons that could signal dark matter annihilation in nearby galaxies or galaxy clusters. The James Webb Space Telescope, with its unprecedented infrared sensitivity, is opening new windows into the early universe when the first dark matter structures were forming. By observing the most distant galaxies ever seen, Webb can study how dark matter halos influenced galaxy formation in the cosmic dawn, when the universe was less than 1 billion years old. These observations provide crucial tests of our understanding of how dark matter shaped the earliest phases of cosmic evolution. Webb's infrared eyes can peer through cosmic dust to see the first stars forming within dark matter halos, revealing how these invisible structures guided the ignition of stellar nurseries in the primordial universe. The telescope has already discovered galaxies that are larger and more mature than expected at such early times, challenging our models of how quickly dark matter halos could assemble and begin forming stars. Theoretical research into dark matter continues to explore new possibilities for its fundamental nature. Beyond the traditional candidates like neutralinos and axions, physicists are considering more exotic possibilities: dark matter particles that interact with each other through hidden forces, creating complex dark sectors with their own rich physics; primordial black holes formed in the early universe that could account for some or all of the dark matter; even more speculative ideas involving extra dimensions or modifications to the fundamental laws of physics. Each of these theoretical possibilities makes different predictions for how dark matter should behave in different astrophysical environments. Sterile neutrinos, for example, would produce distinctive X-ray signatures when they decay. Axions might be detectable through their conversion to photons in strong magnetic fields. Self-interacting dark matter would create cores in galaxy halos, rather than the steep density profiles predicted by standard models. By comparing these predictions with increasingly precise observations of galaxy rotation curves, galaxy cluster dynamics, and large-scale structure formation, astronomers and physicists are gradually narrowing down the viable options for dark matter's true nature. Each new observation adds constraints to the theoretical models, slowly guiding us toward the truth about this cosmic mystery. The cosmic microwave background, the afterglow of the Big Bang, continues to provide crucial insights into dark matter's properties. The precise patterns of hot and cold spots in this ancient light carry detailed information about the conditions that existed when the universe was only 380,000 years old. By analyzing these patterns with ever greater precision, cosmologists can determine the amount of dark matter in the universe, its clustering properties, and even potential interactions between dark matter and ordinary matter in the early universe. The Planck satellite, which completed its observations in 2013, provided the most detailed map of the cosmic microwave background ever created. Its measurements confirmed that dark matter makes up about 26.8% of the universe's total energy density, while ordinary matter accounts for only 4.9%. The rest is dark energy, the mysterious force driving the accelerated expansion of the universe. Future cosmic microwave background missions, with even greater sensitivity and resolution, promise to reveal new details about dark matter's role in the early universe. These observations may detect the subtle signatures of dark matter interactions, dark matter decay, or even the effects of dark matter streaming motions that could provide clues to its particle nature. The study of gravitational waves, ripples in space-time itself, is opening entirely new avenues for dark matter research. When black holes merge, they create gravitational waves that carry information about the masses and properties of the merging objects. If some black holes are actually made of dark matter or formed from dark matter concentrations, their mergers might have distinctive signatures that could be detected by current and future gravitational wave observatories. The LIGO and Virgo gravitational wave detectors have already revealed a universe filled with merging black holes and neutron stars, but they represent just the beginning of gravitational wave astronomy. Future space-based detectors like LISA will be sensitive to much lower frequency gravitational waves, potentially detecting the mergers of massive dark matter structures or other exotic phenomena related to the invisible universe. Some theoretical models predict that dark matter could form its own black holes through gravitational collapse, creating objects that would be distinct from black holes formed by stellar collapse. These primordial black holes could have a wide range of masses, from microscopic objects smaller than atoms to giants more massive than our Sun. If they exist, their mergers would create gravitational wave signatures that differ from those of ordinary stellar mass black holes. As we continue our gentle drift towards sleep, surrounded by the invisible presence of dark matter, we can marvel at the extraordinary progress that has been made in understanding this cosmic mystery. From Zwicky's pioneering observations in the 1930s to today's sophisticated experiments and simulations, each generation of scientists has added new pieces to the puzzle, gradually revealing the hidden architecture that shapes our universe. The cosmic web that dark matter has woven connects every corner of the observable universe, linking the smallest galaxies to the largest superclusters through an invisible network of gravitational influence. Along this web, matter flows and structures evolve, following patterns established by dark matter's patient work over billions of years. We are part of this grand design, our existence made possible by the invisible scaffolding that supports all visible matter. The dark matter particles that pass through us every second carry with them the history of the cosmos, the memory of structure formation, the accumulated wisdom of billions of years of cosmic evolution. They connect us to the cosmic web, to the invisible architecture that makes our existence possible. In a very real sense, we are made of star stuff, but we exist because of dark matter's patient work in creating the gravitational wells where stars could form. The interplay between dark matter and ordinary matter creates a cosmic ecology of extraordinary complexity and beauty. In the dense cores of galaxy clusters, hot gas glows with X-ray light as it falls into dark matter potential wells. Along cosmic web filaments, streams of cool gas flow toward galaxies, fueling the formation of new stars. In the vast voids between filaments, space is nearly empty, containing only a sparse network of dark matter and the occasional isolated galaxy. This cosmic ecology is constantly evolving as dark matter halos grow through mergers and accretion. When two galaxy clusters collide, their dark matter halos interact primarily through gravity, while their gas components collide violently, creating shock waves and turbulence that can be observed across the electromagnetic spectrum. These cluster mergers are among the most energetic events in the universe since the Big Bang, releasing energy equivalent to billions of supernovae. The Milky Way itself is part of this ongoing cosmic evolution. Our galaxy is slowly cannibalizing its satellite galaxies, stripping away their stars and incorporating them into its own structure. The Sagittarius dwarf galaxy, for example, has been orbiting the Milky Way for billions of years, gradually losing mass with each pass through our galaxy's disk. Eventually, it will be completely destroyed, its stars scattered throughout the Milky Way's halo. This process of galactic cannibalism is guided by the distribution of dark matter in our local cosmic neighborhood. The Milky Way's dark matter halo extends far beyond the visible galaxy, creating a vast sphere of gravitational influence that captures passing objects and draws them into decaying orbits. Over cosmic time, this process has helped our galaxy grow from a small seed in the early universe to the magnificent spiral we see today. The future evolution of our cosmic neighborhood is also shaped by dark matter. In about 4.5 billion years, the Milky Way and Andromeda galaxies will collide and merge, an event that will be choreographed by the gravitational dance of their dark matter halos. Computer simulations of this future merger show a complex sequence of close approaches and separations before the two galaxies finally settle into a single, massive, elliptical galaxy. During this merger, the dark matter halos will interact first, passing through each other and gradually spiraling inward due to gravitational friction. The visible components of the galaxies will follow more chaotic paths, with stars being flung into long tidal tails and streams. Despite the violence of the collision on galactic scales, the chances of individual stellar collisions are vanishingly small due to the vast distances between stars. This future merger represents just one event in the ongoing evolution of dark matter structure in our local cosmic region. The local group itself is part of the larger Virgo supercluster, which is slowly collapsing under its own gravity. Over tens of billions of years, the galaxies in our cosmic neighborhood will gradually merge into ever larger systems, guided by the invisible hand of dark matter gravity. But this process of structure growth is competing with the accelerating expansion of the universe driven by dark energy. As space itself expands faster and faster, it becomes increasingly difficult for gravity to pull new material into existing structures. The era of vigorous structure formation is coming to an end, and the universe is entering a new phase where existing structures evolve more slowly, while the overall expansion carries everything farther apart. This cosmic transition from a structure formation-dominated era to an expansion-dominated era represents one of the most profound changes in the universe's history. It marks the beginning of the end for the active, dynamic phase of cosmic evolution and the start of a much longer, quieter period where change happens more gradually. Dark matter will continue to shape the evolution of individual galaxies and galaxy clusters, while dark energy increasingly dominates the expansion of space itself. The ultimate fate of dark matter depends on its fundamental properties, which remain mysterious despite decades of research. If dark matter particles are truly stable, they will persist long after all the stars have burned out and all the black holes have evaporated through Hawking radiation. The cosmic web will remain, its invisible filaments stretching across an increasingly empty universe, a monument to the universe's active phase. If dark matter particles can decay, however slowly, they might eventually disappear, leaving behind only the ordinary matter that we can see. Current observations suggest that dark matter particles, if they decay at all, must have lifetimes much longer than the current age of the universe. But given enough time, trillions upon trillions of years, even the most stable particles might eventually succumb to decay processes we don't yet understand. As we settle into the peaceful conclusion of our journey, we carry with us the profound realization that we are explorers of the invisible, seekers of the hidden architecture that shapes reality itself. The dark matter that fills the universe is not separate from us, but intimately connected to our existence, our planet, our galaxy, and our cosmic destiny. The mystery of dark matter remains one of the greatest challenges facing modern science, but it is also one of the most beautiful and inspiring. It reminds us that the universe is far stranger and more wonderful than we can imagine, filled with invisible realms and hidden connections that challenge our understanding of reality. Every answered question reveals new mysteries. Every solved puzzle points to deeper layers of cosmic architecture waiting to be explored. In the gentle quiet of this moment, let yourself drift into the vast spaces between galaxies, where dark matter streams flow like invisible rivers through the cosmic web. Feel yourself becoming part of this grand architecture, your consciousness expanding to encompass the hidden structures that connect every corner of the observable universe. The dark matter particles that surround you have been traveling through space for billions of years, witnesses to the entire history of cosmic evolution. They have seen the cosmic web take shape, the slow assembly of structure through billions of years of gravitational attraction and merger. They have guided the formation of our own galaxy, the birth of our solar system, the emergence of life on Earth. As sleep begins to embrace you, imagine yourself floating weightlessly through the cosmic web, surrounded by the invisible architecture of dark matter. Feel the gentle pull of gravity from distant galaxy clusters, the subtle flow of dark matter streams carrying you along paths carved out over billions of years. You are part of this grand cosmic dance, your consciousness expanding to encompass the hidden structures that connect every corner of the observable universe. The dark matter halo that surrounds our galaxy extends its invisible embrace, a sphere of mysterious particles that have been shepherding the formation of stars and planets for nearly 14 billion years. Within this halo, you are safe and supported, held in the gentle gravitational embrace of matter that reveals itself only through its caring influence on everything around it. Let your awareness drift outward, beyond the confines of our solar system, beyond the disk of our galaxy, into the vast, spherical halo of dark matter that extends for hundreds of thousands of light years in every direction. Here, in this invisible ocean, dark matter particles move in slow, ancient orbits, their paths shaped by the gravitational memory of cosmic time. As you float through this dark matter sea, you encounter streams of particles flowing inward from the cosmic web, carrying with them the building blocks of future structure. These streams merge and separate, creating complex patterns of flow that have been developing since the universe was young. You are witnessing the patient work of cosmic architecture, the slow construction of the invisible framework that supports all visible matter. Feel yourself becoming one with this cosmic dance. Your consciousness is expanding to encompass not just our local dark matter halo, but the entire cosmic web that stretches across the universe. Along the filaments of this web, dark matter flows like cosmic rivers, connecting galaxy clusters separated by hundreds of millions of light years. At the nodes where these filaments intersect, new galaxies are being born from the collapse of primordial gas clouds, their formation guided by the invisible scaffolding of dark matter. The cosmic web is alive with motion, though this motion unfolds on timescales far longer than human experience. Dark matter halos grow through the accretion of smaller structures, each merger adding new complexity to the gravitational architecture. Galaxy clusters form at the largest nodes, their hundreds of member galaxies bound together by the gravitational influence of dark matter that outweighs them by factors of 10 or more. As you drift through this invisible universe, you begin to appreciate the profound patience of cosmic structure formation. The dark matter particles around you have been moving through space for billions of years, following orbits that were established when the universe was a fraction of its current age. They have witnessed the birth and death of countless stars, the formation and evolution of galaxies, the slow dance of cosmic expansion that carries everything ever further apart. Yet through it all, the dark matter has remained constant, providing the stable gravitational foundation upon which all change and evolution can occur. It is the eternal backdrop against which the drama of cosmic history unfolds, the invisible stage upon which the visible universe performs its magnificent dance of creation and destruction. Let your consciousness expand even further, encompassing not just our local cosmic neighborhood, but the entire observable universe. Here, the cosmic web reveals itself in all its glory, a vast network of dark matter filaments connecting billions of galaxies across distances that challenge comprehension. Each galaxy is a node in this web, each star a tiny spark of light, illuminating the invisible architecture that makes its existence possible. The cosmic microwave background, the afterglow of the Big Bang, carries within it the imprint of the tiny fluctuations that would eventually grow into this magnificent structure. Those fluctuations, variations in density of only 1 part in 100,000, were the seeds from which the entire cosmic web would grow. Dark matter's gravitational influence nurtured these seeds, allowing them to grow into the complex hierarchy of structures we observe today. As you float through this cosmic architecture, you realize that you are not separate from it, but intimately connected to it. The atoms in your body were forged in the hearts of stars that formed within dark matter halos. The calcium in your bones, the iron in your blood, the oxygen you breathe. All of these elements were created through stellar nucleosynthesis within galaxies that could not have existed without dark matter's gravitational scaffolding. The planet beneath you orbits a star that formed within our galaxy's dark matter halo, its position and motion determined by the gravitational influence of invisible matter. The solar system itself is carried along by the galaxy's rotation, following an orbit that takes it around the galactic center once every 230 million years. All of this motion, all of this structure, all of this cosmic choreography is guided by the invisible hand of dark matter. In this moment of profound cosmic connection, you understand that the mystery of dark matter is not a problem to be solved, but a wonder to be appreciated. The universe has chosen to reveal itself to us gradually, allowing us to discover layer upon layer of hidden complexity and beauty. Each new discovery opens up new questions. Each answered mystery points to deeper mysteries waiting to be explored. The search for dark matter continues in laboratories deep underground, in space-based observatories scanning the cosmic web, in computer simulations that model the evolution of structure over cosmic time. Each experiment brings us closer to understanding the true nature of the invisible universe. Each observation adds another piece to the puzzle of cosmic architecture. But perhaps the greatest discovery is not what dark matter is, but what it teaches us about our place in the cosmos. We are not observers standing outside the universe looking in, but participants in the grand cosmic dance. Our very existence made possible by the invisible scaffolding that shapes everything around us. We are children of the cosmic web, our atoms forged in stellar furnaces, our planet formed from the debris of ancient supernova, our lives sustained by the stable gravitational environment that dark matter provides. As you drift deeper into peaceful sleep, let yourself be carried along by the gentle currents of dark matter that flow through the cosmic web. Feel yourself becoming part of this grand architecture, your consciousness expanding to encompass the hidden structures that connect every corner of the observable universe. The dark matter particles that surround you have been traveling through space for billions of years, and now they cradle you in their invisible embrace. The cosmic web extends its filaments across the universe, connecting galaxies separated by vast distances, channeling the flow of gas and energy that powers the formation of new stars and planets. Along these filaments, dark matter streams carry the building blocks of future structure, the raw material from which new galaxies will be born in the distant future. At the nodes where these filaments intersect, massive galaxy clusters shine like beacons in the cosmic web, their hundreds of member galaxies bound together by the gravitational influence of dark matter halos that extend for millions of light years. These clusters are the cities of the cosmos, bustling with activity as gas flows in along the filaments and ignites to form new stars. Between the filaments stretch vast cosmic voids, regions of space where dark matter and ordinary matter are spread incredibly thin. These voids are not empty, but contain a delicate tracery of structure, like soap bubbles in a cosmic foam. The boundaries between voids and filaments are where much of the universe's star formation occurs, as gas is compressed and heated by the gravitational influence of the cosmic web. As you float through this invisible architecture, you are witnessing the universe's grandest construction project, the slow assembly of cosmic structure that has been ongoing for nearly 14 billion years. Dark matter provides the blueprints and the building materials, while ordinary matter adds the finishing touches that make the structure visible to our eyes. The dance of dark matter continues on every scale, from the smallest subhalos to the largest superclusters. Within our own galaxy, dark matter substructures create subtle variations in the gravitational field that influence the orbits of stars and gas clouds. Some of these substructures are the remnants of smaller galaxies that were torn apart by the Milky Way's gravity, their stars scattered into streams that wrap around our galaxy like ribbons. As sleep embraces you more fully, let your consciousness expand to encompass the vast scales of cosmic time and space. Feel yourself becoming one with the dark matter streams that flow through our galaxy, the invisible rivers that carry the memory of cosmic evolution. The particles that surround you have witnessed the entire history of the universe, from the first moments after the Big Bang to the formation of the first stars and galaxies. They have seen the cosmic web take shape, the slow assembly of structure through billions of years of gravitational attraction and merger. They have guided the formation of our own galaxy, the birth of our solar system, the emergence of life on Earth. They continue their patient work even now, maintaining the stable gravitational environment that allows stars to shine and planets to orbit in peaceful regularity. The dark matter halo that surrounds the Milky Way extends far beyond the visible disk of stars, creating a vast sphere of gravitational influence that has been our cosmic home for billions of years. Within this halo, you are safe and protected, held in the gentle embrace of forces that operate on scales far beyond human experience, yet intimately connected to your daily existence. Every breath you take, every heartbeat, every thought you think exists within this invisible architecture. The atoms in your body were forged in stellar furnaces that could only exist because dark matter carved out the gravitational wells where gas clouds could collapse and ignite. The planet beneath you orbits a star that formed within our galaxy's dark matter halo, following patterns established by invisible forces operating over cosmic time. As you drift deeper into the peaceful realm of sleep, carry with you the profound realization that you are not separate from the universe, but intimately connected to its deepest structures. The dark matter that fills the cosmos is not alien or distant, but part of the very foundation that makes your existence possible. You are a child of the cosmic web, a conscious observer of the universe's hidden architecture, a participant in the grand cosmic dance that has been unfolding for nearly 14 billion years. The mystery of dark matter surrounds you with its invisible presence, connecting you to every corner of the observable universe through gravitational threads that bind all things together. In this moment of perfect peace, you are one with the cosmos, your consciousness expanded to encompass the hidden structures that shape reality itself. The universe holds you in its gentle embrace, the same forces that guide galaxies and galaxy clusters also cradling you in restful sleep. Dream of dark matter, streams flowing through space like cosmic rivers, carrying the building blocks of future structure to distant realms. Dream of galaxy mergers unfolding over hundreds of millions of years, choreographed by the invisible hand of gravitational attraction. Dream of the cosmic web itself, that magnificent architecture of filaments and nodes that connects every visible galaxy to the invisible foundation that makes it possible. The dark matter particles that surround you are ancient and eternal, carriers of cosmic memory, witnesses to the universe's long history of growth and change. They connect you to the beginning of time and the far future, to the smallest scales of particle physics and the largest scales of cosmic structure. In your peaceful rest, you become part of their eternal dance, your consciousness merging with the invisible currents that flow through the heart of reality itself. Sleep now in the knowledge that you are held safely within the universe's grandest architecture, the dark matter framework that shapes everything we see and everything we are. The cosmic web extends its protective embrace around you, its invisible filaments carrying you gently through the night toward whatever wonders tomorrow may bring. You are part of the cosmos, and the cosmos is part of you, connected forever through the hidden threads of dark matter that weave the fabric of existence itself. Rest peacefully, cosmic explorer, knowing that the universe continues its ancient work around you, the patient construction of structure and beauty that has been ongoing for billions of years and will continue for billions more. The dark matter that fills the cosmos is your cosmic companion, the invisible presence that makes all visible wonder possible, the hidden architecture upon which the magnificent symphony of existence plays its eternal song. In the gentle embrace of the cosmic web, in the loving arms of invisible matter, in the patient care of forces beyond human comprehension, yet intimately connected to human existence, sleep comes as naturally as starlight, as peacefully as the slow rotation of galaxies through the vast spaces of the universe. Dream well, child of the cosmic web, as the dark matter streams carry you safely through the infinite night of space and time.